Welcome to Investigating the Universe. In this episode, we're delving into a mind-bending concept that has perplexed philosophers, physicists, and thinkers for centuries. The idea that time, as we commonly perceive it, might not truly exist. We often find ourselves racing against the clock, trying to squeeze more hours into the day. But have you ever stopped to consider what time actually is? From the moment we wake up to the moment we go to sleep, our lives revolve around hours, minutes, and seconds. The ticking of a clock or the change of date on a calendar gives us a sense of order, of continuity. But what if this is all an illusion? What if our perception of time is merely a construct we've created for practical purposes? Could it be that time, in its purest form, is not a fundamental truth of the universe, but merely a tool we use to make sense of our existence? Could it be that our perception of time is more of a practical construct than a fundamental truth? Philosophers throughout history have grappled with the nature of time. To truly understand this conundrum, let's journey back to ancient Greece. Parmenides, a pre-Socratic philosopher, proposed that reality is unchanging and indivisible, implying that time, as a measure of change, is an illusion. This bold assertion was a radical departure from the conventional wisdom of the era. Fast forward to the 18th century, and we encounter Immanuel Kant, a central figure in modern philosophy. Kant postulated that time is not an entity or substance to be measured, but rather a system of perception. In other words, it's not that time exists independently, but we humans impose a temporal structure on our experiences. In the late 19th and early 20th centuries, the British philosopher J.M.E. McTaggart shook the philosophical world with his theory of time. McTaggart proposed two series of time, the A series, which includes the past, present and future, and the B series, which consists only of earlier and later relations. He argued that while we perceive time as the A series, this perception is illusory. Time, according to McTaggart, is truly the B series, which does not involve change. These philosophical perspectives have laid the groundwork for our modern understanding of time. They've challenged us to question our perception and consider the possibility that time might not be a fundamental aspect of reality, but a construct of the human mind. Each of these philosophers, from Parmenides to McTaggart, brought unique insights to the table, pushing the boundaries of our understanding and setting the stage for scientific theories that would further probe the nature of time. Their ideas continue to inspire and challenge us today, reminding us that the quest for knowledge is an ongoing journey, full of unexpected twists and turns. In the grand scheme of things, the philosophical exploration of time isn't just about understanding the cosmos, it's about understanding ourselves. After all, the way we perceive time shapes our experiences, our decisions, and ultimately our lives. These philosophical perspectives have laid the groundwork for our modern understanding of time. Albert Einstein's theory of relativity revolutionized our understanding of time. This extraordinary theory, born out of Einstein's brilliant mind, presents an intriguing concept known as time dilation. Now, imagine you are aboard a spacecraft traveling close to the speed of light. According to Einstein, you would experience time at a slower pace compared to someone stationary on Earth. This means that if you embarked on a 5-year space journey at near light speed, upon your return, you could find that decades or even centuries have passed on Earth. This is not the stuff of science fiction, but a real consequence of Einstein's relativity. But the story doesn't end with speed. Gravity also plays a role in the dance of time. Picture a massive star or even a black hole, objects with enormous gravitational pull. Time, as perceived by a distant observer, would appear to slow down significantly near these massive objects. This is known as gravitational time dilation. The concept of time dilation paints a picture of a flexible, malleable time, one that can stretch and compress depending on where you are and how fast you're moving. It's a far cry from the unyielding, uniform time we experience in our day-to-day lives. These ideas have been tested and confirmed. From experiments with high-speed particles to precision measurements with atomic clocks on airplanes and satellites, the predictions of Einstein's theory have been verified with astounding accuracy. Einstein's relativity gives us a universe where time is not absolute but relative, a universe where time can slow down or speed up. It's a universe where the ticking of a clock is not just the rhythm of a mechanical device, but a melody played on the fabric of space-time itself. This suggests that time is not as fixed as we might think. It's a profound shift in perspective, one that challenges our everyday experience and opens the door to a universe far more fascinating and complex than we could have ever imagined. In the quantum realm, time takes on a different character. Here, the standard rules of physics that we're accustomed to don't apply. Instead, we have a realm where everything is governed by probabilities and uncertainties. This is the world of quantum mechanics, a branch of physics that describes the behavior of particles at the smallest scales. Let's dive into one of the most peculiar phenomena in quantum mechanics: quantum entanglement. It's the strange, counterintuitive phenomenon where two particles become intrinsically linked, regardless of the distance between them. Once entangled, the state of one particle instantly affects the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously described it, seems to defy our understanding of time and space. Then, there's the Heisenberg uncertainty principle, another cornerstone of quantum mechanics. This principle states that it's impossible to simultaneously measure both the position and momentum of a particle with absolute precision. The more accurately we know one of these quantities, the less accurately we can know the other. This inherent uncertainty introduces a fundamental fuzziness into the quantum world, which again challenges our conventional understanding of time. Is time just another quantum variable, bound by uncertainty? Or does it play a more profound role in the quantum world? These are the questions that physicists are still grappling with. Quantum mechanics also offers tantalizing hints of time's potential reversibility. In the quantum realm, certain processes can theoretically run backward, defying the forward march of time we observe in our everyday lives. Could this be a clue that time, as we understand it, is merely a construct? These quantum quirks further challenge our conventional understanding of time. They suggest that time might not be a fundamental property of the universe, but rather an emergent phenomenon, rising from the complex dance of quantum particles. As we delve deeper into the quantum realm, our understanding of time continues to evolve, leading us into ever more mind-bending territory. Some theoretical models propose that time might be an emergent property of a deeper reality. This intriguing idea nudges us to reconsider our conventional understanding of time. Imagine, if you will, a cosmic stage where the actors are not stars, planets, or galaxies, but rather more fundamental entities. These entities interact, dance, and weave together to create the fabric of reality as we know it. In this grand cosmic dance, time might not be a fundamental player, but rather a byproduct, an emergent property that arises from the interactions of these foundational elements. Let's consider a familiar example from our daily lives: temperature. Temperature is not a fundamental property of a single molecule, but arises from the collective behavior of a group of molecules. Similarly, time might emerge from the collective behavior of deeper, more fundamental elements of reality. Theoretical physicists have been developing models to explain this concept. One such model is the holographic principle, which suggests that our three-dimensional reality, including time, might be a projection of information encoded on a two-dimensional surface. Another model, known as loop quantum gravity, proposes that space and time are composed of tiny, indivisible units, much like the pixels on a screen. In this model, time emerges from the dynamic interactions of these quantum loops. These models are still in the realm of theoretical physics, and much work remains to be done. But they offer tantalizing glimpses of a universe where time, as we know it, might be an emergent phenomenon rather than a fundamental aspect. So we are left to wonder, could time be merely an emergent property, not a fundamental aspect of the universe? The quest to unravel the mystery of time continues, pushing the boundaries of our understanding and challenging our assumptions about the very nature of reality. As we conclude our journey, we ponder the profound implications of a universe where time might not be what it seems. This concept is not just a philosophical or scientific curiosity, but it greatly impacts how we view the world and our place in it. If time is not fundamental, but an emergent phenomenon, it suggests that our universe is far more intricate and mysterious than we ever imagined. It challenges our conventional understanding of reality and compels us to question the very fabric of our existence. The idea of time as an illusion is a revolutionary thought, one that could potentially alter our perception of everything around us. It opens up a myriad of questions about the nature of the cosmos, our role within it, and the endless possibilities that lie beyond our current comprehension. If time is but an illusion, perhaps the true essence of the universe is even more astonishing than we can imagine. Please consider liking and sharing this video, and of course hitting that subscribe button to stay connected with Investigating the Universe.